I'd like to introduce Dr. Andy Sessler. We're very lucky to have with us today to tell us about 75 years of accelerator physics at Berkeley Lab. Dr. Sessler got his undergraduate degree at Harvard in 1949 and his PhD from Columbia in 1953, and he joined the physics department of Ohio State University the year after that. But it was when he came to Berkeley Lab in 1962 that he decided that he didn't need to travel any farther, and he's been here ever since. He's not only a distinguished scientist emeritus at Berkeley Lab, but also the director emeritus, having been the director of the lab from 73 to 1980. And if you look up the history of the lab that we've been doing in episodes in The View and is now posted on the 75th anniversary website, you'll see that you'll get some idea of how pivotal Dr. Sessler's directorship was, because he turned the lab in a whole new direction of service to society, with a particular emphasis on halting the deterioration of the environment. It seems all the more remarkable then that until that time, Dr. Sessler had worked in atomic physics, nuclear structure physics, elementary particle physics, low temperature physics, and especially in accelerator physics, which he still does today. He's in the Accelerator and Fusion Research Division, and that was one of three divisions that resulted from the innovative programs that he himself started at the lab as director, the other two being the Earth Sciences Division and the Environmental Energy Technologies Division. Dr. Sessler is the co-author of over 400 publications. He's been active in professional physics affairs throughout his career. He's won a slew of awards, including DOE's E.O. Lawrence Award, and he's a member of numerous honorary societies, including the National Academy of Sciences and Sigma Xi. As an activist and a leader in arms control and human rights, he's made his mark well outside the field of physics as well. He's served in several posts for the Federation of American Scientists, including chairman. He co-founded the human rights group Scientists for Sakharov, Orlov, and Sharansky, SOS, for which he received the American Physical Society's first Michelson Medal. Is that right? I should have worn my glasses. The first medal for humanitarian service in 1994. And in 2000, he was the chairman of the report on technical aspects of the proposed national missile defense by the Union of Concerned Scientists. It's an honor to welcome Dr. Andy Sessler.
Turn this on. Thank you much. After that introduction, whatever I say is bound to go down, but well, we'll try. Okay. We're celebrating the 75th anniversary. Here's a picture of E.O. Lawrence, 1930. Here was the first cyclotron, 5 inches in diameter, a tiny little thing. Here was the original rad lab on campus next to LeConte Hall, where the chemistry building now is. And here is Don Cooksey and E.O. Lawrence on the 60-inch cyclotron. In this talk, I want to go beyond the provincial view, if you will, that it all happened in Berkeley, and set into proper historical perspective, as proper as I can make it. And different guys in the question period can have all kinds of opinions. I want to put into the context of work of E.O. Lawrence and the cyclotron boys, and I will do this by tracing the development of particle accelerators. Actually, particle accelerators started with some theoretical work in the early 1920s, and the first accelerator producing nuclear reactions, which was a motivation, a reason for building accelerators, was in 1931. So it's exactly 75 years of history that we should be reviewing. The first motivation, as I said, was from Ernest Rutherford, who desired to produce nuclear reaction with accelerated nucleons. He was very tired of using natural radioactivity to try to see a nuclear reaction. From that time on, many decades, the motivation was to get to ever higher beam energies. At the same time, and especially when colliding beams became important, there was a desire to get to ever higher beam current, and not only energy, but current. In the last decades, and I would say in the last 3 decades really, the motivation has been from the many applications of accelerators, such as producing X-ray beams, medical needs, ion implantation, spallation sources, and on and on. And I'll tell you a little about that, but not so much, because that's really the future or the present. Here are the major nuclear advances in the 1930s, at least in my opinion. First was accelerators producing nuclear reactions, Graaff and Walton, 1932. Then there were accelerators producing radioactivity, the Curies in France. Then there was slow neutron reactions, which Fermi in Italy. And then there was nuclear fission, Otto Hahn, and today Strassman would certainly be included in the Nobel Prize, and probably a second prize would be given to Lisa Meitner and Otto Frisch for figuring out what they were observing. None of these advances were in Berkeley. Unfortunately, there was too much focus in Berkeley on machine development, and I could go into some embarrassing stories about how Lawrence went to the Solvay conference in 1933 and presented a lot of actually wrong results. However, for just that, namely cyclotron development, Lawrence received the Nobel Prize, and today Stan Livingston would be included. Stan Livingston was the graduate student who actually built the cyclotron and made 2 major contributions, which I won't just detail here, without which the cyclotron wouldn't have worked. And Stan was a very modest person, but years later he said, Lawrence was my teacher when I built the first cyclotron. He got a Nobel Prize for it, I got a PhD. So what I would like to do is tell you something about various kinds of machines, and we'll go through quickly. I mostly have pictures, and I have lots and lots of pictures, and I'll keep my eye on the clock, and then I'll go faster and faster, but we'll leave out some. I have to go faster and faster because I can't skip. There's really no harm done. So let's start with the first accelerator that produced nuclear reactions was a voltage multiplying column that Graaff and Walton built from 1930 to 32. A small voltage was applied to a series of condensers, and then they were fired in series, and that produced a large voltage. At about the same time, Van de Graaff developed the idea of mechanical belts, turning mechanical energy into electrostatic energy. Here's a picture of Walton. You see him hunched down here in the corner, and he's actually observing. And one of these guys came to Berkeley about just before the observation, and he said, "There's no doubt that we'll get there first." And this was remarkable because the cyclotron was giving 1,000 times as much intensity as the Graaff-Waltons were, but they understood experimental techniques. Here's a modern Graaff-Walton. Well, it's not really modern because nowadays we don't build them anymore, but in 1960 that was a very modern one, probably one of the most modern ones ever built. Van de Graaff, as I said, made machines. He started he did work in Princeton and at the Terrestrial Magnet Lab in Washington, D.C. Then he moved to MIT, and he got this big experimental station, and you see these 2 very large Van de Graaffs, and a voltage was developed between them. Well, under normal operations, there were no sparks because you were building up voltage. But this was, as you saw, in a hangar. And there were lots of pigeons. And this is an example of what happens when you have pigeon droppings coming on these nice smooth spheres, which are perfectly designed to hold the voltage. It was soon appreciated that negative ions could be accelerated by a positive electric column. Then they could be stripped of their electrons and then repelled by this column. So you get twice as much energy for the same amount of voltage. And Louis Alvarez called these Swindletrons, and they were later called tandems, and they're now in common use and generally are made, commercially made. Here's a picture of one at Oak Ridge National Lab. The negative particles are excited, pulled up to the top of this thing. It's about 100 feet high. Then there's a magnet that turns them around. They're stripped, and they're sent down this column. And so they get twice the energy. Sometimes they're built horizontally, actually, but here's one that was vertical. Cyclotrons. I would like to talk about, well, these four things. So we all know that Lorentz invented the cyclotron and made a succession of cyclotrons. Perhaps his greatest contribution was really the creation of a laboratory where physicists, engineers, biologists all worked together to achieve far more than any one discipline could accomplish, and we like to think that's what we're doing even today. Cyclotrons are still built for nuclear physics and medical purposes, but certainly not for high-energy physics. Here's a picture of an 11-inch cyclotron. I think I can go reasonably quickly. Here's a picture of this 1939 of the 60-inch cyclotron. Transverse focusing of particles was developed actually by Stan Livingston on the original cyclotron and was crucial in making the very first cyclotron work. And he also realized how to remove the accelerating field foils and thus increase the intensity by what is a magnitude. These were the two things I alluded to, contributions. Longitudinal phase focusing was developed just after World War II independently by Ed McMillan from this lab and Vladimir Vexler. The concept really made the 184-inch work. As you know, the 184-inch was started against the good advice, or bad advice, of theorists. Hans Bethe, for example, wrote a paper showing that it would never work. Lorenz's response was there are many ways to skin a cat. I don't quite know what cats had to do with this subject. Here's a magnet of the 184-inch cyclotron, which is located just up the hill. At the time, the 184-inch was started just before World War II and was turned into electromagnetic separation of the isotopes of uranium as part of the war effort. So this first use, actually, long before it became used in nuclear physics, was to separate isotopes of uranium. And the first demonstration was made here, and then Oak Ridge was established, set up, built with 1,000 Calitrons in the name, California Calitrons. And Louis Alvarez had long, wonderful stories about how he was, for example, sent to Oak Ridge to get it going. They couldn't make it work, and he got it going. And all the material for the Hiroshima bomb was electromagnetically separated. There were other methods, but they weren't very good, and some of them were used as preliminary methods, but then the uranium was fed into electromagnetic separation, and that was the final method that was used. And this method has not been used at all since World War II. It's too expensive and too difficult, and as we all know, centrifuges nowadays are the method of choice. Here's a Calitron, actually. And this is an early version. Actually, the later versions were lying down, not vertical. In the early 50s, just after the development of strong focusing, described in a moment, it was realized by the Midwestern Research Group, Miura, that it was possible to have many different configurations of an accelerator. And some of these configurations were advantageous for various purposes. In particular, they developed the idea of fixed field alternate gradient accelerators, that is, fields which didn't vary in time and had a large acceptance. So you could put in particles of one energy, and finally you get out particles of a higher energy. This result, for example, this is used in spiral sector cyclotrons. Our 88-inch cyclotron is based on this idea. And today, various other applications are being considered. Here's a spiral sector model, the very first spiral sector model built by the Miura group in Wisconsin. And you can see the spiral magnets there. That's the very first one. Now, of course, we have gigantic machines. Here's one of the gigantic machines, Triumph, which is the world's largest cyclotron in Canada. And the machine is still in operation. In fact, it was just upgraded with a new LINAC, and so it can accelerate rare isotopes, that is, radioactive isotopes. So the LINAC makes particles which would decay after a short time. They put into this cyclotron and accelerate it to higher energies. Linear accelerators. We're going to talk about protons and heavy ion, induction LINACs, and electron. Proton, heavy ion LINAC. Louis Alvarez was the first one to make a linear accelerator that only involved a single frequency. Prior to that time, people had made linear accelerators, but you needed a different frequency for every a part of it. He made a tank which had only one frequency, but made different lengths of drift tubes. And in the 1960s, RFQs were invented in the Soviet Union by Teplakov, and actual construction was pioneered by a group at Los Alamos. Here's a picture of the first Louis Alvarez LINAC built just after World War II. And he was going to use spare parts that came from the war effort for radar. In fact, he never used these. So the frequency, the choice of frequency was matched to this, but in fact, he never used them. In the early 50s, at the time when the Betatron was being constructed, Lawrence had the idea of producing nuclear material with a large accelerator. That they would make neutrons. It's sort of like a spallation neutron source way before its time. Here you can see this gigantic machine. And this was at a time when people were concerned that there wasn't enough uranium in the United States to build bombs. So the purpose of this machine was to produce nuclear material. Many people were sent out there, and as a result, the Cosmicron was completed before the Betatron, because the Betatron was stopped in its tracks while this was built out at what is now Livermore site. The building is still there, actually. It's the biggest building at the site. The machine had uncontrollable sparks and never produced anything. Here's a picture of a radio frequency quadrupole, and these are the simple, except they're very elegant, beautiful machining, and couldn't have been built in the old days because you had to have wonderful ability to calculate, first of all, and then actually to machine these parts. But once you could do that, they can replace the large Cockcroft-Walton machine, a picture of which I showed you. And in fact, that's been done throughout the world, so that Cockcroft-Waltons are no longer built. RFQs are used. Induction LINACs. They were first invented by Christophilus at Livermore for magnetically confined fusion. He wanted to make an electron. He wanted to have a lot of electrons and make an electron cylinder around which he would then have ions and fusion. That didn't work, of course. Then we in Berkeley took this idea and developed an accelerator for electron ring accelerator. That's another idea that didn't work. Then it was used to study implosions, nuclear implosions at Livermore, and then finally at Los Alamos. And these new machines are all based on what was developed at LBL for the electron ring accelerator. And it's also been the basis for work on heavy ion fusion. This program has been terminated by the US government. We don't need energy, everybody knows that. The world's first induction accelerator, Astron, built at Lawrence Livermore Lab in the late 50s and 60s by Nick Christophilus. And you can see massive ion that went into this. Here is a more modern, this is the FXR, built at Lawrence Livermore. And it's made in order to study, it makes X-ray. You accelerate electrons, you bang them into the target, you make X-rays. Because you can make very short pulses, you can take pictures of the implosion process actually during the process, because typically that's a shake or 10 to minus 7 seconds, and you can easily make beams that are much shorter than a nanosecond is typical, so 100 times shorter. Most recently, under the stockpile stewardship program, there's been a lot of interest in weapons that are no longer cylindrically symmetric. That is, suppose you get a rust spot on one side, then you need, so then the weapon may or may not work. And so you need to be able to look in 3 dimensions, if you will, to not assume cylindrical symmetry. And so Los Alamos has built a DART facility, and actually much of that was made here and then moved into Los Alamos and still is being run in. And so here you see a picture, and you put a nuclear weapon just where these 2 buildings come together. A nuclear weapon without the nuclear material. The electron linacs are based on a high-powered klystron, which was invented during World War II by the Varian brothers and Ed Ginson for radar. In fact, it never was used for radar at that time. Magnetrons were used. But now it's used all the time for electron linacs. And a succession of machines were built, finally culminating in a 2-mile accelerator at SLAC. It's interesting that Louis Alvarez bet Bill Hansen that it was impossible to build an electron linac. This based on Louis's work with protons and the successful building of a proton linac. In fact, of course, electron linacs can be built, and so here's the SLAC site. Well, it's close by. You all know the SLAC site. Betatrons. Very few Betatrons are built these days, but at the time, around 1940s, they were very important. For they provided the only way to accelerate electrons to higher energy than could be obtained with electrostatic machines. Many physicists had tried to make circular electron accelerators, but they all failed until Don Kirst was able to make a Betatron by careful attention to orbit dynamics. This was almost the first paper in which people really worried in detail. There's a famous paper by Kirst and Serba. And during World War II, one of these early machines was actually used at Los Alamos. So here's a picture of one of the first Betatrons. It's actually not the first, but one of the first, built in the early 50s. And this is a so-called 20-inch machine at the University of Illinois. And then a larger machine, 100 MeV Betatron. Don Kirst went to GE for a year or 2, and he started this machine, and then actually he went back to Illinois, and this machine was completed after he was there. Nowadays, compact, here's a picture of a commercially produced Betatron, very compact, and they're used to X-ray, to look for defects in forging, steel beams, ship hulls, all kinds of things. So they're useful devices, actually. I mean, that's very compact, easy way to make very intense X-rays. Synchrotrons. The first synchrotron was really made possible by the idea of Ed McMillan's idea of phase focusing, of handling the longitudinal dynamics, and the concept of strong focusing, and the concept of cascading synchrotrons. For example, at Miura, we felt that was not a good idea. Up until about 1959, we felt that it would be impossible to take a beam out of one accelerator and put it into the next in an efficient way. And of course, that's now quite possible, so we have synchrotrons cascaded one after another. The first proposal, even before the invention of strong focusing, was by Mark Oliphant, and essentially all accelerators are based on the synchrotron principle. Here's the first synchrotron. This was in England. They had built a Betatron to X-ray unexploded bombs falling on England. And later, Frank Goward converted the Betatron into the first proof of principle synchrotron. So this was actually the very first. Here's a 300 MeV electron synchrotron built by GE. And you can see the bright flash of a beam synchrotron radiation actually emerging. The first observation of synchrotron radiation was just by the decrease. It was in a ceramic chamber, so radiation didn't come out. And so they measured that the orbit was decreasing, and therefore there must be radiation. The same thing was done as astrophysics for binary stars and won a Nobel Prize for Taylor and Halsey. No observation of gravitational radiation, but an observation of the change in the trajectory of particles. Okay, but very soon it was observed. This was the first synchrotron that was actually planned, 1 GeV machine at Birmingham. It took a very long time to be built, and inadequate attention was paid to the safety, radiation. This was in the basement of a lecture hall, and so it only could be run at night and hardly ran at all. This was the first proton synchrotron to be brought into operation, and as I said, the Betatron might have beaten this out, but the guys were busy building the MTA. And this is our Betatron, which is about to be dismantled at great cost. And somewhere you can see the man on the left. It says, oh yeah, he's standing on the concrete shielding up there. Strong focusing. Ernie Courant, Hartland Snyder, Stan Livingston revolutionized accelerator design in the early 50s. It allowed small apertures. The Betatron aperture was so large that it was called a Jeep accelerator. They had to put the windshield down, but otherwise it would take a Jeep. The concept was independently discovered by Nick Christophilus, but we only know that after the fact. His discovery had no impact on the world. Building on this idea of strong focusing, then the Miura people, for example, in the Midwest had developed fixed field alternate gradient accelerators and many other things. The CERN people in Switzerland switched. They were going to build a weak focusing machine, but they learned about strong focusing from the Americans, and they switched their design. And there's a picture of in '57 during construction of the PS. And as we all know, the PS is still going on, and it's the starting point of many, many accelerators. Even it will be for the LHC. And here's the AGS at Brookhaven. Fermilab made a superconducting Tevatron, and that can be seen in the very bottom of this picture, below the reds and the blues, which are ordinary room temperature magnets. And all this is based on the synchrotron principle, now using strong focusing and cascading synchrotrons, so you have a first synchrotron and a second and a third. All right, I'd like to talk now about colliders. And I'll talk about early colliders, proton, antiproton colliders, and a little bit about future machines. In the 50s, a number of places, Miura, Novosibirsk, so Miura in the Midwest, Novosibirsk in Russia, CERN in Switzerland, Stanford, Frascati in Italy, and Orsay in France, developed the technology of colliding beams. And I would say that Bruno Tuschek and Gersh Brudker and Don Kurz were the people who really made this happen. And colliders are now the devices employed to reach the highest energy, and almost all machines are colliders. Here's a picture of the very first electron-electron storage ring in the early 60s in the Heppel Laboratory on the Stanford campus. And this machine took 6 years to run in. Many problems were discovered one after another and solved on this machine, after which it then became more routine to build colliders. This was the beginning. And I remember very well, I used to go down there one day a week and work on this with them. This is the first electron-positron storage ring, AUTA, The picture's taken about 1960. This was built in Frascati, Italy, but then they moved it to France to have a more powerful source. In Italy, it was horizontal, and you injected electrons on one side, then you moved it over, and you injected positrons, the same linear. In France, it was made vertical, and no, maybe I have it backwards. Maybe, in any case, it didn't work. And the reason it didn't work was that when they flipped it, I guess in France they did some flipping rather than just moving horizontally. And the flipping made some dust come down and wiped out the beam every time. And so it took them some time to figure out what was going on. This was one of the first large electron-positron storage ring at Donley in Frascati in Italy. You can see the very large RF cavity sitting in the middle, about to be installed. Superconducting RF cavities at the CERN, at LEP, Large Electron Positron Collider. So here we see the introduction of superconducting RF, and of course that was pioneered in many different places, at Stanford, at Heppel, in CERN, in DAISY. And KEK was the first accelerator to put a superconducting RF in a major way. In the 1960s, CERN decided to try to build a proton colliding beam machine, an intersecting storage ring, or ISR. And this was really the first time that anybody had attempted to build a large proton colliding beam machine. There were many uncertainties. Could you hold a beam that long? Could you stack a beam? So on. There were really deep questions. And they built a small model to study this, and this is a picture of that small model. Here you see the actual ISR, which was built in, like, Kjell Janssen led the group, and you can see how massive this is. The machine, Kjell's philosophy was to do everything that was ordinary in this machine super well, so that if we had any problems, we could then immediately address them, and we would know it come from the colliding beams. That philosophy turned out to be very good, because one of the problems was, in fact, related to vacuum, and vacuum had to be increased about 1,000-fold, and the machine was so well built that one could actually do that. So, all right. Unfortunately, very little physics was discovered on this machine, primarily because, I could say, other guys will say different things. I think the experimentalists were not looking in the right place. Simon van der Meer had the idea of stochastic cooling. He wrote a little report on CERN in which he apologized for writing this report. He said it was well known, but people had urged him to write it down, so he did. And of course, he won a Nobel Prize on the basis of this report. His work on stochastic cooling made proton-antiproton colliders possible. There was a lot of consideration at Fermi Lab. It was rejected as being too radical an idea, but CERN went ahead. And of course, as a result of this, they discovered the W and the Z, won Nobel Prizes, and so on. Here's the original. So before they did this, they wanted to test out whether you could really cool beams, stochastically cool beams, and this was a ring that they took the magnets from the old G-2 experiment and used them. Here's a modern picture. Fermi Lab then got into the game. Too late, but into the game anyway. And here's a P-bar source built in the 90s. And the stochastic cooling is unbelievably effective by some measure, namely the density and phase space, which is the proper measure. The cooling is by a factor of 10 to the 11th. It's unbelievable, really, how effective this cooling is. And that's, of course, what made P-bar colliders possible. The Large Hadron Collider, LHC, is under construction at CERN. And this machine is 28 kilometers in circumference, talking big machines. And it's supposed to be finished in, what, 1 year or 3 years? I can't remember exactly. Rick relativistic heavy ion collider is in operation at Brookhaven. And that's really a further development of studies that started here in Berkeley on the Bevel-Lac in the late 70s and then led to studies on other machines, even at Brookhaven, at CERN, and then finally the building of a collider. All this previous work was not with colliders, but regular, just an accelerator on target. And here you see a picture, which we all know, nuclear matter under extreme conditions. So this is a collision of gold on gold, and the temperature is 2 trillion degrees, and as many as 10,000 particles are born. So measuring all these and observing and working out whether you have a quark-gluon plasma, and if you do, what is its nature, is quite a challenge. And as you know, people have suggested now, there's good experimental evidence that it behaves more like a liquid than you would have expected. Synchrotron radiation sources. About 1970, accelerators built for high energy physics were used parasitically. And I know there were, it's certainly, that was done at SLAC, at CEA in Cambridge. They wanted to convert the machine to a synchrotron radiation machine. And I remember an NSF panel that reviewed this field and felt that there was no need for 2 machines in the United States. There were very few users at that time. So it was decided that it would be better to do it at SLAC, where there's a good injector, and one could be confident that they would have a better facility. And that was probably the right decision, but it's interesting to look back, because now there are these machines built all over the world, more than 50 of them. Last time I looked, it's probably up to 60 or 70 by now, and they're machines in all the countries of the world. And in the United States, there are machines in Brookhaven and SLS. They've just been given $800 million to improve them, to build a second machine. Argonne has the APS, which is a very big machine. SLAC has SPEAR, and now the LCLS, linear collider light, LINAC collider light source is under construction. And of course at LBL we have the ALS. Here's a picture of Grenoble in France. So this was the European synchrotron radiation facility. That was at 6 GeV. The Argonne APS came in later. It was at 7 GeV. Then the Japanese built a facility at 8 GeV, Spring 8. And nobody's built a higher energy machine since then. This is an interesting political thing. As you know, the Germans have given their synchrotron radiation facility, their old machine, basically, to the Middle East. And after much discussion, Jordan has decided to host it. And here we see the King of Jordan discussing this with scientists. And actually, this machine will be open to all users, so Israel, Arabs, all nations. This machine it was decided not just to move the machine, but to use that as an injector and build an even better machine. And efforts are underway to get adequate money to do that. The linear coherent light source at SLAC and the European Union X-ray free electron lasers have both been made possible by the invention of FELs, free electron lasers, which was Stanford, John Mady, in the late 70s, and the invention of photocathodes, which was a Los Alamos thing in the 80s. The European device has actually worked. It's been renamed. It's called Flash, and it's actually given off some X-rays. And here is a picture of the DAISY free electron laser, magnetic wiggler, which is used to wiggle the electrons to get ever more radiation from them. Let's talk about cancer therapy machines. The first treatment by Lawrence, actually, Lawrence and his brother, John Lawrence, Ernest and John, of their mother. Their mother was diagnosed as having a cancer. And they got a machine, and they put her in front of her, and they put her in front of it, and she was cured. There's some question about whether it was a misdiagnosis or not, but anyway, the fact that she was cured motivated them to continue to work on this. Stone in the late 30s, and right here actually, did a lot of work with irradiating patients with neutrons without adequate attention to the long-term effects. The neutrons were fine. They would immediately reduce the cancer, but then the long-term effects were very serious. All the patients essentially died, and that really stopped the use of neutrons for about 30 years. Linacs for X-rays were built, well, in this country by Siemens and Varian. Hadron therapy, use of the Bragg peak. So with X-rays, the radiation is most intense as you come into a body and drops off, so you have to irradiate from many directions. With hadrons, the radiation is almost negligible and then very big right where the tumor is, and you can control the position and the depth by energy and position with magnets. So hadron therapy would seem to be more advantageous. That was first suggested by Bob Wilson in '46, and it was pioneered here and at Harvard. And now there are 5 facilities in the US. The first one was Loma Linda and in Los Angeles. The second one is Mass General. Then there's one in Harvard, Indiana, Texas, and there's now talk of quite a number of others. These are all proton machines. Heavy ions were carefully developed in the 70s, from basic biology all the way to patient treatment. You may remember that we had a building here with patient rooms and patients and it was supposed to be reasonably pleasant for patients. Right now there are no such. It was determined that carbon was best if you go through all the periodic table. As you go through the periodic table, the Bragg peak becomes better, but soon you get to the point where the nucleus can pick up electrons or not, so that you can't determine with precision the depth in which you want to treat the tumor. So carbon seems like the best. And based on that, a dedicated facility was built in Japan. And now in Japan, they're essentially putting one into every state. So there's interest in Europe. Most patients, however, are treated by X-rays. Here's a picture of a system from Varian. The Linac is in the top. There's a rotating gantry. You see this pointing right down at the patient. They don't do that nowadays because now there's good evidence, for example, that women who had breast cancer in the 60s and 70s, I just heard a 2-hour talk on this, who had breast cancer in the 60s and 70s were treated with radiation, and there's now a good study of what is their likelihood that they would have cardiac problems, and it's like 40% higher than normal. In other words, the radiation that treated the cancer, the tumor in the breast went on and caused cardiac problems. Nowadays, they treat from the side. So this rotates around, and the Linac is actually, that makes the X-ray. So it's like a dentist machine. The Linac makes electrons bang into a target, you get X-rays, and the X-rays come down or from the sides. And they're very sophisticated machines that you can determine the field. It's all computer controlled. They're really very beautiful and very reliable and very safe machines. Here's a picture of the Japanese facility. And they actually have 2 synchrotrons, and they synchronize with the respiration so that you can tell exactly where the tumor is. And of course, there's much sophisticated techniques now of using beams where you come into the tumor and you get radiation back so you know exactly where the tumor is and so on. So that we go on and on, but we won't. All right, what about the future? Well, there's certainly the International Linear Collider that people hope to build. There's spallation neutron source that's actually been constructed already in the United States, and there's one under construction in China and talk in Europe. There are rare isotope accelerators. The next thing in nuclear physics would be a machine that accelerates all different kinds of radioactive species, and I told you about how some is done at Triumph, but even more. And the Germans, with their FAIR project, are really moving ahead on that. And of course, there are neutrino superbeams and neutrino factories, and way in the future, muon colliders, accelerators for heavy ion fusion, proton drivers for power reactors. So you can make a power reactor which is not critical, below criticality. So there's no danger of it running away and causing an explosion. And then you feed in with an accelerator, which you can turn on or off, and you bring it above criticality. And so there's talk of that kind of thing. And of course, in the long term, lasers and plasmas. So in conclusion, what were the accelerator milestones through the years, at least as I see them? Well, we've sort of talked about them. Cockcroft-Waltons, Van de Graaff, cyclotrons, synchrotrons, strong focusing, FFAG, proton Linacs, electron Linacs, heavy ion accelerators, induction Linacs, space charge effects. By that I really mean the whole theoretical basis that goes with all this accelerator development, single particle and many particle dynamics. Cooling methods. I mentioned stochastic. I didn't mention electron cooling. Electron cooler has just been put in on the Tevatron, and the people at Brookhaven are building a cooler to cool RIC that has to be 100 times more powerful than the one that at the Tevatron. So the challenge is there. Colliding beams of protons, electrons, protons and antiprotons, RFQs, we're doing away with these great Cockcroft-Walton machines, FELs, which is the basis of all the modern synchrotron radiation facilities that people are talking about for the next generation. Essentially all of them involve free electron lasers. Photocathodes, which made that possible. Various medical applications, which I talked about. Superconducting magnets, superconducting RF, light sources, and insertion devices. So I've tried in this overview to put the contributions of Lawrence and his co-workers into perspective. In doing that, I might have led you to conclude that I'm a supporter of eliminating Lawrence, a commonly used name. Nothing could be further from the truth. I believe that Lawrence, besides his invention of the cyclotron, made contributions to science of great significance. And speaking personally, at least, I honor his contribution in this lab and try always to use Lawrence Berkeley as our common name. So we've seen the saga of particle accelerators from the very beginning through the present. And perhaps this was just a passing moment in the history of mankind. But I think it's much more likely to be an activity that will continue on into the future. I think we can expect accelerators not only to produce physics, but also to fill an ever-increasing catalog of applications, which are already and will further enrich our everyday lives.
Andy, I'm happy to report that the Department of Energy did not terminate heavy ion fusion program here. It's fair to say what they did is they severely directed our attention to near-term target experiments, which actually are pretty good for our program, but they don't mean to preclude heavy ion fusion in the future.
Well, it's almost a nuance between you and me. Okay, accepted.
Andy, can you comment on the state of accelerator-driven energy production, particularly fission energy production, using subcritical systems, and is it being pursued vigorously, and if not, why not?
All right, it's being studied rather vigorously, and actually I'm going to go visit a place in Japan where they have a nuclear reactor, and they are studying just this in Osaka, part of the JERI, the Japanese. So that is being thought about. Excuse me. I guess the idea is that we're going to need nuclear energy. I better get a drink of water here. And that there are other ways to make reactors that are critical and adequately safe. So that's the view that most of the world takes. There's a possibility. There's a possibility excuse me, of burning up nuclear waste using, well, you could use accelerators, and that was one idea that's been pushed by the Japanese and also by Los Alamos. Now there's the idea that and this is part of the global nuclear partnership that the president just announced, there's a possibility of using reactors to burn up the nuclear waste. So here you would burn up the actinides, and also you would take the ordinary uranium-238 out of the waste stream. So you would cut the waste stream, excuse me, you cut the waste stream by a very large factor. So therefore, Yucca Mountain, you wouldn't need many Yucca Mountains. Just one Yucca Mountain would take care of all our needs for hundreds of years. So that's the first step in the reprocessing is to take out the uranium-238. The second step is to burn up the actinides, which would reduce the need to isolate these nuclear wastes from hundreds of thousands of years to hundreds of years, which is a very big difference. So all these things are being worked on quite vigorously.
So there was, and I think still is, this machine in Russia, in Dubna. So I don't remember the name, I should remember, but I remember that it used to be quite an important device. So could you put that into perspective, comparing to the ones you've talked about?
All right, well, there was the old phasotron, but I don't know if that's what you're alluding to. And that was a machine built during the Cold War, and it was suddenly the largest machine in the world. And the President of the United States met with some physicists. Can you imagine the President meeting with physicists? I know what you're thinking, but still, any president, to discuss what should be done. And actually, Argonne was commissioned to build a machine as quickly as possible of higher energy than the phasotron. And that machine, of course, the AGS was under construction, but that used strong focusing, and these higher up guys didn't believe in strong focusing. So the idea was to simply scale up the Betatron. Well, there was already a Jeep accelerator. You couldn't quite scale it up. So people built the ZGS, and actually that came in long after the AGS. But all right, different story. I don't know if that's the machine you're alluding to.
There was one area of accelerators where Berkeley has played a big role, and it was missing in your list, and that is in terms of the ion sources, both heavy ion and negative ion,
yes.
So forth. I know you can't fit everything in,
Yeah,
but
that's true.
Berkeley was a big contributor in the early times in those areas.
I agree. I thought this question period would mostly be comments like this. You left out that, you left that. Thank you.
Andy, I just wanted to point out that the event you showed from Rick was a technology invented here at LBL, the TPC detectors.
Yes, sure. That. I didn't talk about detectors.
And you also didn't mention anything about the asymmetric colliders.
About the which?
Asymmetric.
Yeah, no, that's true.
Which is also was invented here at Berkeley.
Enthusiast for bee factories. I recognize it.
Well, I think probably we can conclude unless there's any other questions. So join me in thanking Dr. Sessler.